Well, I'm sure you all are having a worthwhile time here. Uh, Moving on to our next speaker is Mr. Anup Changaroth, Director Portfolio Marketing APAC Ciena Corporation. As Director Portfolio Marketing at Ciena, Anup Changaroth is responsible for marketing the company's portfolio of next generation optical. His topic today is towards data center without walls. Businesses are looking for ways to move expenses from a capex to an opex model, and one way is through the evolution of data centers into cloud services. Through this talk, you can learn how inter-data center networking tailored to high-demand cloud infrastructure requirements enables a virtual data center without walls, a new approach to IT services. Please join me in welcoming Mr. Anup Changaroth.
Yes? Okay. How's everyone doing? Good, excellent. So the topic for today's session is this thing called Towards the Data Center Without Walls. I just flew in from Seoul, Korea, just this morning actually. I flew into Singapore. And when I was in Korea this week actually, I had dinner with one of my colleagues, and I mentioned that I was coming to Bangalore, and he asked what I was going to do, and I mentioned I was going to present about data center without walls. And his first response was, oh, you guys are looking to build data centers in the Arctic so that you will use the natural cold air and the natural dryness of the air to cool the data centers? Is that what data center without walls was? And I said, no, not quite. This, by the way, is a picture of the supposed Facebook data center in the Arctic, which hasn't quite been built yet. With the way the stock is hitting, I'm not sure they're going to be able to build it. But anyway, so what is data center without walls? Before I go into that, let me just sort of briefly talk about who Ciena is. Ciena is a very focused company on what we call the converged packet optical portfolio. When I say converged packet optical portfolio, it is really about photonics. It's about Ethernet. It is about transporting packet traffic and TDM traffic and OTN traffic and video traffic and fiber channel traffic across a photonic fabric. And you saw from the previous speaker, he used the word fabric. Fabric is a common term that's used in the industry to imply a network infrastructure that works quite seamlessly and quite reliably. That's what a fabric means. That fabric could be an Ethernet fabric, like he mentioned. It could be a fabric of a photonic switches across the network. So that's typically what people call by a fabric. So what Ciena does is we build photonic networks. Just to give an example, Reliance, the Reliance backbone in India, the entire Reliance backbone network across all of India runs on Ciena optical networking technology. It all runs on 40 gig capacity links. So there's multiple wavelengths. The wavelengths are transported over fiber optic cable. And those wavelengths today, already in India, are running at 40 gig capacity, each of those wavelengths. And you have multiple wavelengths over fiber today. So we're well beyond 10 gigs already in core network capacity. And at Ciena, we've gone beyond that. We've deployed 100 gig. Today, 100 gig is very popular among customers, deploying 100 gig for terrestrial networks, for submarine networks. Even in India, we've already done a number of trials of 100 gig capacity links. So when the previous speaker talked about data centers between long distances over kind of virtual data centers, that is a reality already. And today's talk is really to kind of give you an idea of how some of those pieces really kind of work together and the reality behind it. Okay? All right. So just to kind of set the stage a little bit and perhaps step back a little bit and to give you an understanding, a basic understanding of what are the fundamental drivers behind this momentum. I think most of you already recognize that the cloud adoption is really driven by economics, right? At a fundamental level, why are people using the cloud? Why are they moving to a cloud-based environment as opposed to building their own data centers, building their own hardware? They're moving towards that kind of environment because it brings about some specific economic benefits, right? That's the fundamental question. The issue is that economic benefit, where is that economic benefit coming from? Is it because it's cheaper hardware? Is it because it's consolidated? Yeah, That's the bottom line, right? The bottom line is that as you consolidate your data centers into a single location, as you start to utilize those equipment in that consolidated data center to a much more efficient manner, you are leveraging the efficiency of a shared networking or shared hardware environment or shared software environment. It's that sharing, the utilization improvement comes from that sharing concept, right? That's the basic idea. Within a single data center, within what we call an intra-data center, it's easy to understand. You have hardware with servers and you virtualize it. But what happens across data centers, right? The key question is, most businesses, most international businesses, they have offices in the US, they have offices in Asia Pacific, they have offices in Cala. They can't afford to have just one consolidated data center. It's got to be multiple data centers because they have people working in different geographic regions, right? And if you want the right response from an application standpoint, you can't have a user sitting in the US trying to access an application in Asia over long distances and assume that he can get the same performance. So the question comes to, is a cloud a data center that is consolidated, or is it distributed, or is it a combination of the both? That is a fundamental question that many enterprise customers are asking today. They recognize that they need to consolidate data centers. Within Asia Pacific, if they had 50 data centers today, they're consolidating it to 3 or 4, but they recognize they need to have that 3 or 4, and they need those 3 or 4 to provide the end users, regardless of where that end user is, the same level of performance that they were getting when the data center was local to them, right? So that's a fundamental question, and that's what's been driving our strategy of data center without walls, and I'll explain some more. The key thing to keep in mind is, as you start to consolidate data centers, and you recognize and you acknowledge that you need to have a few data centers that are as close to your users as possible, you start to hit a scenario where you've got intra-data center traffic that's moving around. I think the previous speaker talked about virtual machine migration. He talked about it in the future tense. I can tell you that virtual machine migration happens today in a huge amount today already. People like Google, people like Amazon, and a whole bunch of people are already doing massive amounts of virtual machine migration on a daily basis, What's interesting, though, is if you look at the performance of virtual machine migration, the virtual machine migration performance as in terms of how the machine migrates from one site to another site is highly dependent on the actual network connectivity. The physical network connectivity that connects the two data centers together has a direct impact on how well the virtual machine migration happens. The charts that you see here, the diagrams that you see here, shows the latency, the effect of latency, packet loss, and the actual bandwidth of the links between the data centers, and the effect that it has on virtual machine migration. So in the example of the first graph on the top left, for example, as your latency between your data centers, as the latency increases, you go from 0.5 milliseconds to 1 millisecond to 2 milliseconds and so on, you start to see a non-linear effect on the virtual machine migration. What this means is that if your networking performance, your connectivity between the data centers isn't a very high performance network connection, your virtual machine migration is going to start to have major issues, and your users are going to start getting affected. The applications, the real-time applications, or even if it's not real-time applications, if you need to migrate virtual machines, they're going to get impacted by the latency caused by the network connectivity between data centers. Similarly, the effect of packet loss, you see a very similar trend. It's a non-linear effect, and the effect of bandwidth in terms of how fast the virtual machines migrate and the pause times, the response pause times between the actual migration itself. So bottom line, the message here is, in order for you to have virtual machine migrations operating in an optimum manner, you have to be very, very careful how your network is connected between each other. The physical connectivity between the data centers cannot be over traditional legacy type of networks. Specifically, router-based networks, IP/MPLS-based networks have huge amounts of latency inherent in the way that packets get routed across the network. And those kinds of latencies can kill your business services. Okay. So you understand the concept and the economies of consolidating the data centers. You recognize that you can't consolidate to just one data center. You've got to have multiple data centers that are as local as possible to your subscribers. And in fact, what you will find is that most large-scale data center or cloud providers have a significant amount of data centers. Even within a single metro, they may have 2 or 3. Within a country, of course, they have much more. If you look at people like Google, they have massive amounts of data centers all over the place. In Asia Pacific, they have at least 8 that are spread across different countries. So this is the kind of a typical scenario of the data center. What you see in this diagram is, what this diagram is showing is the different level of utilization of that individual data centers. For example, data center 4 has a very high utilization. It's almost fully utilized. Versus data center 5, which is maybe half utilized. This is a natural tendency of how subscriber traffic comes into the network, and the actual data center utilization varies from region to region, right? What we are trying to do is consolidate and allow the data centers to operate as if it was one virtual data center. So the level of efficiency that you get out of this is significant. It's significant, okay? The key thing to keep in mind, and most people don't recognize this instinctively, when you look at a cloud service provider, the user-to-cloud traffic versus the cloud-to-cloud traffic, the data center to data center traffic, anyone has a guess on what the ratio is? User-to-cloud versus cloud-to-cloud, or data center to data center. What the ratio of traffic is? Anyone with a guess? No? Most people would imagine that the user to data center traffic was significantly more than the data center to data center traffic. That's not the case. It's a 10-to-1 ratio. There is 10 times more traffic between data centers than there is from the users to the data center. Why is this? Because there is a lot of background things that are happening. Replication of information that's going on, virtual machine migration that's going on, data dumping that's going on, backup that's going on. There's huge amounts of data that's going on between the data centers. So you start to recognize that the connectivity between the data centers is a vital, vital part of any service provider that's offering a cloud service across a large geographic region. Okay. So why Ciena? Why can't any other vendor who provides DWDM, transport, and wavelength? You know, there are lots of vendors. You know, there's at least 15, 20 vendors who supply these types of equipment today. What makes Ciena different? Why is Ciena more applicable to what I just talked about? Well, there's 3 real factors. And these 3 factors are, perhaps some of you are not that familiar with it, but I'll try and explain what this is. The first one is something called coherent transport leadership. Traditional DWDM transmission, the way that you send a light wave or a wavelength across from point to point, across distances, whether it's a metro distance or a long-haul distance, was done through a technology known as direct detect. What direct detect means is that you switch on your laser, you switch off your laser, and you do it at 10 gigabits per second, and you get your information being transmitted at 10 gigabits per second from one end to the other end. That's like doing Morse code. You do dot, 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 dash, 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 dot, 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 similar to Morse code. And that's how DWDM transmission has been for the last 15, 20 years. In 2008, Ciena pioneered this technology called coherent transport. It is essentially taking technology from FM radios and bringing it to the optical domain. What it means is that we no longer send bits in terms of switch on, switch off. We actually use digital signal processing, and we send it through algorithms, and we transmit the algorithms. And on the other end, the receiver takes that algorithm, and it takes it back, and it converts it back into the actual information. And why do you want to do that? Because you can use mathematics to increase the bit rate substantially. You can go from what used to be 10 gig to 40 gig, and now 100 gig, and we've already started to demonstrate to customers 200 gig and 400 gig transmission. This is 400 gigs per wavelength, right? So you can have, in a single optic fiber, you can have as many as 88 wavelengths. So imagine 400 gig times 88 is what a single fiber optic cable can carry. That's the kind of capacity that we're talking about. And this is reality. This is what's happening already today. Okay? So the fundamental thing about coherent technology is that not only does it increase the transmission rate substantially, but it also fundamentally changes the way that service providers build photonic networks. In the past, photonic networks had to have a lot of static elements in the network that you can't change. What that static elements mean is that you can't change the way the light wave travels. You can't dynamically reroute wavelengths across the network. They are fixed, and they're fixed for 15, 20 years, right? With coherent transmission, you can literally change the wavelength. Today he's going this direction, tomorrow he can go in a different direction, and you don't have to change anything else in the network. It becomes a lot more dynamic. The network at the photonic level becomes hugely dynamic. And that is exactly what you need to be able to cater to the kinds of traffic that you see between data centers. When a data center has a sudden spike in requests for stuff, he needs capacity coming in and going out. He can request for wavelengths to come in and go out. Right? So that's number one. Number two is something called the optical control plane. So I'm sure many of you are familiar with control plane. Control plane has been around in routers for the longest time. You know, OSPF, BGP, all these are control plane technologies. But in the photonic and the optical arena, control plane is not the norm. It didn't really exist very much. Ciena has had control plane technology in our hardware since 2001, and we've been shipping this for a long time. We've had a lot of experience. Why is this important? Because when you connect a network infrastructure into a cloud system, a cloud operating system, you need the network to be able to understand the demands that are being requested of it. And in order to do that, you need a control plane that can take those demands and those requests and redirect resources in the network, redirect wavelengths, redirect bandwidth across the network. So that control plane becomes a fundamental element. And the previous speaker talked about SDN networks, software-defined networks. That software-defined networks is exactly what control plane does. The requests coming in from external sources, whether it is a cloud OS or whether it's another equipment, requesting for bandwidth, and your network being able to react to that request. The third one is what we call high reliability and low latency solutions. So as you start to imagine the interconnectivity between the data centers, you start to realize that if you had just one physical link between two data centers, and if that fiber got cut, and as you guys are probably well aware, in India, fiber cuts is a daily occurrence. You need networks that are highly robust. In other words, you need what we call mesh networks. The networks are no longer just a ring or just point-to-point. They are actually meshed together. They're meshed in a multi-connected fashion. And so if there's one fiber cut, traffic can get rerouted across alternate path. If there's another fiber cut, traffic gets rerouted again. As long as there's some way to get between two nodes that need connectivity, you can get to them. And that control plane is a key element of that. Control plane helps determine how this traffic gets rerouted, but that reliability function is a key element. As well as low latency. I talked about the impact of latency in terms of the performance of virtual machine migrations. Latency is a critical element of how this whole thing has to come together, right? So these three key elements, if you look at the other vendors in this market space, none of them have all these three key elements there today. So we are well ahead of the other vendors in this particular space. Okay, so Ciena's, where do we play in the cloud? I think I kind of explained it, so I'm not going to spend too much time. But in essence, we really play between data center connectivities, whether that's in the metro, regional, long haul, ultra long haul. Today, we are already deploying over 9,000 kilometers. So what we call trans-Pacific distances. We're deploying 100 gig capacity over trans-Pacific distances. That's probably a lot faster than what you're getting from your metros in India today. Okay, so how does this all kind of fit together? In essence, all the stuff that I talked about, the coherent transport technology, the control plane technology, the mesh networking capability, the low latency stuff, that all fits into the actual network infrastructure combined with what we call a hypervisor. And this is the hypervisor that you're familiar with. It's you could term it as a middleware. That middleware allows us to connect into a cloud OS and be able to be the intermediary of any request that comes in from the cloud, whether it's a request for bandwidth or whether it's a request for a route that has the lowest latency or a request to shut down certain parts, for example. This is the layer that actually does that for us. And it essentially sits right above the network, and it sends control signals across the network to create those kinds of paths as necessary. And it does this dynamically, of course. Okay. Just to give you an example that this is not science fiction, it's actually real stuff that's happening. This was done last year. In fact, it's almost a year ago. It was done in Dublin by the TM Forum. I don't know how many of you are familiar with TM Forum. TM Forum is a non-profit organization of service providers that come together to help each other from a business services and a business solutions perspective and economics perspective. They kind of look at all the advanced solutions. And in essence, together with the TM Forum and EMC, we actually worked on an actual live demo that showcased exactly what we talked about. Using EMC's vPlex system, Ciena's network hypervisor, and the actual cloud itself. I don't know if you can see from the back, but there's some animation in this network diagram. Through the cloud OS, we can request capacity to be established between the two data centers, an enterprise data center and a service provider data center. So this is a hybrid scenario, a private cloud bursting across to the public cloud when he's requesting for some additional resources for storage, for example. We can set up a FAT pipe between the two locations, and the data dump can happen over the FAT pipe. So this could be a raw dump that happens across maybe at the end of the day. And then after that raw dump has happened, we shrink that down to just a thin pipe so that they can keep themselves synchronous, updated, for example. And then if there's a virtual machine migration request coming in, we can set up another FAT pipe for the virtual machines to migrate, and the virtual machines then migrate with high performance, low latency, and all those attributes that I talked about. And once they've migrated across, we can shut that link down again. And this happens in real time. In real time, depending on the users that are requesting certain resources in the network, and they need to move the virtual machines across from their own cloud across to the service provider cloud. And this was actually demonstrated to customers. We actually demonstrated, the TM Forum helped us set it up, and we actually demonstrated it across to customers. Okay, so the previous speaker talked about this VM migration happening in the future. It's actually literally happening today. We continue to get customers, customers like Google, for example, talking about this because they have huge amounts. Every 4 hours, if you didn't know, every 4 hours there's a lot of synchronization that happens on a global basis between their virtual machines across the globe, across their different data centers. That's huge amounts of capacity that goes on with these kinds of virtual machine migrations. Okay, with that, I pretty much had come to the end of my presentation. Any questions? Yes. This slide?
Mic there, please, and please increase this volume also.
Oops, no, it doesn't work. You want to shout a little bit louder, maybe? Typical scenario of how a hybrid scenario would work, right? So this enterprise customer has his own private cloud. He's got a set of resources. He's got his own data center. He recognizes that his data center, he's cost optimized it so that on a regular basis, it has adequate resources to provide him with all the computing and storage requirements that he needs on a regular basis. But at the end of the month, when he's doing his or maybe at the end of the quarter, when he's doing his quarterly financials, he suddenly has an extra set of resource requirements that he has no resources for, and he's wanting to burst from the public cloud. Typically what happens is that enterprise customer already has an established relationship with the public cloud. He would already have a physical link that connects his private cloud to the public cloud. It could be, for example, a 100 gigabits Ethernet link. But that 100 gigabit Ethernet link will not be utilized at 100 gig all the time. He may be utilizing on usage basis at maybe 10 meg or 1 gig on a regular basis. But when he's bursting at a high capacity, he would automatically up his transmission on that 100 gig link because he's got the physical link. He would up the rate to 100 gig to burst, and that would be billed by the public cloud at a later stage, at the end of the month or whatever. So the physical connectivity is there, but the actual consumption of capacity is not there unless he needs it, right? The key thing to keep in mind, though, is even though the physical connectivity between him and his first connection point, the first point of contact, that physical connectivity is there, within the service provider's domain, he may not provision 100 gig capacity there all the time. right? He has to then demand capacity on triggered capacity through the system when he needs to between his locations, right? This is typically the service provider. This cloud, this blue cloud that you see here is typically the service provider's network that connects the service provider's data center to the enterprise customer's cloud. Does that make sense? Any other questions? Yes. 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 Oh, yes. I wouldn't say not advocated. It has an inherent disadvantage compared to photonics. Yeah. Yes. Yes. Uh-huh. Correct. Yes. Right. So it's a good point. So there's CAC mechanisms within the control plane technology that exists within the platforms. There's CAC, connection. What's a full term for CAC? CAC is a mechanism to check whether there's adequate capacity before you establish a connection. So there's CAC mechanisms that go on in the network itself as part of the control plane. That's one aspect. The other key aspect is obviously in a disaster scenario when fibers are cut, inevitably you're going to have some people that will not have capacity to go over the network because you have differences. You have customers who are tier 1 customers who are willing to pay everything or anything to get guaranteed performance, 50 millisecond guaranteed connection. Anytime there's a fiber cut, his traffic is restored within 50 milliseconds, guaranteed. No matter how many cuts that happen in the network, as long as there's some part, he is guaranteed 50 milliseconds. Versus some customers who maybe they want their traffic to be restored if there's one cut, but if there's a second cut, they're not going to pay for the restoration. So the control plane technology that I talked about in my previous slide that we have in our platform actually supports that kind of tiering. We can tier the customer based on multiple criteria, based on how many cuts he wants to experience before he doesn't want to be restored anymore, how fast he wants it, 50 milliseconds or 100 milliseconds or 200 milliseconds or beyond, or whether it's based on latency. We have a lot of financial customers, enterprises who are doing machine-to-machine, what's called high-frequency trading, right? They are machine-to-machine transactions, so they're very, very fast. They need very low latency connections. And what these guys want is that if there's a fiber cut somewhere, when a network is restored, they want to ensure that the restored path has the same latency performance or better than what they had previously. So those kinds of criteria, you can program it in the system, and the control plane has the ability to do that for us. Now, if you look at a typical router, very difficult to guarantee 50 milliseconds. The fundamental difference between the control plane technology in the optical domain and control plane in the router domain is that in the optical domain, it is something that we call deterministic. It operates in a very deterministic manner. A service provider will know if this gets cut, this will get restored in 50 milliseconds, guaranteed, right? Whereas in the router space, it's indeterminate. Sometimes it takes a little longer, sometimes it's quicker. Spanning. We talked about spanning tree, right? Spanning tree is a perfect example. You break spanning tree, it has to reconverge. It could take, depending on the size of the network, depending on the traffic, it could take minutes, it could take seconds, right? Similarly with OSPF and BGP and all that, it could take time. Now, of course, you could argue that MPLS fast reroute is a mechanism to circumvent some of that, but the management overhead of trying to do fast reroute for all these parts and all that is a nightmare. So most service providers don't want to do that. They want a lot of the restoration stuff, the 50 millisecond restoration stuff, to happen at the photonic domain, at layer 1 or layer 0, rather than at layer 3. You follow what I mean? Yes. Yes. Yes, you can, based on the traffic types, for example. So a lot of the platforms that we have, for example, in this diagram, this physical connectivity to this platform is Ethernet. So once you're physically connected with Ethernet, you've got your P bit. You can see what kind of traffic types. You can see the traffic classification. So based on that, you can then decide what to do, whether or not to provide the required level of performance. So it's quite standards-based in that sense. Right? Any other questions?
Yeah. if there are no more questions, thank you so much, Anup, for that wonderful talk. We'd like to offer you a small token of our appreciation from behalf of UBM.